Okay, thanks very much. Well, there's almost as many as I get in my lectures here now, so that's good.
Very popular man.
Okay, well, as it says, dynamic loadings, tidal stream turbines. Certainly not going to take credit for doing any of the work, really. So I will leave that to the accrediting group there. So, underwater wind turbines, that's what they've been called by others. Basically, the physics is the same, with the exception compared to wind turbines. It's a lower velocity average. It's an incompressible fluid, and the fluid density is about 800 times that of air. We use the same characteristic equations. The power coefficient, the torque times the angular velocity over the available energy in the swept area of the turbine. The thrust is just the force that's acting on the body, and then the torque, obviously the alternative force component. In addition to that, what we're also looking at is the momentum coefficient, or the moment coefficient, sorry, which is a result of any bending or asymmetry that's occurring within the turbine blades. One of the issues with this, though, is because of the density, the loading on the tidal stream turbines are quite severe. So we're interested in what's the velocity magnitude. Now, power, great, it's a cubic term. Thrust is a squared term, as is the torque coefficient. So if you get a level of shear through the water column, you're going to have blades that are subjected to a higher velocity at one point than at a lower point. You're going to clearly get a bending moment occurring at the hub root. Wave current interaction. The wave that is 20 meters long, the penetration into the water will be approximately 10 meters. So it's about half the wavelength. That can have a severe effect on loading, depending obviously on the length or depth of the water. Then there's the fact that water doesn't flow in one direction and out the other direction at 180 degrees. So there is a certain amount of misalignment. Should you yaw the turbine into that, or should you leave it go? Depends. Structural interaction. You've got to have a support structure generally. So as the blade passes in front or behind of that support structure, there is then a change in the characteristic for that blade. Background turbulence. Well, turbulence comes in packages generally. Different sizes. You can get a decay from a very large scale down to the very small scale, and depending on what is hitting that turbine would depend on the influence it has on both loading and power output. And then you have the problem when you have a wake. With wind turbines, there's a certain allowance for the wake to impact on a downstream turbine. That is a very unpopular sort of thing to happen in the tidal turbines because of those magnitudes due to the density. So basically it all comes down to, before you put something in the water, understand where you're putting it. It's a fairly obvious statement. So to break it down, I will quote from, check the button, our friend Professor Bahaj, who published this very nice little schematic. Turbulence can be started from either headlands upstream, it can be due to the seabed. If you've got large lumps and divots, it can form very large eddies. If you've got a very rough seabed, you can get a higher amount of drag. That higher amount of drag will actually produce that current profile. And the bigger the profile, the worse you're going to get for any asymmetric loadings. In addition to that, you have this problem with wave penetration. Then you have the wake coming off, all of the structure, and in fact this rotating body. So you end up with a scenario, all of that combined together, and you're going to have a bit of a messy flow that a turbine can be seeing. These tidal roses just show the various angles that you can actually get from different directions. So you can put a turbine in, and throughout the whole tidal cycle, you can actually get variations in the direction that are hitting it. To add complications to that, you do not get waves that are necessarily all in nice straight lines. So how do you cater for that? Just to go to an extreme case, you can get some weird shaped ones, or you can get some that really don't seem to be know what they want to do. You get a more chaotic problem with it. So to combine that all, you've got a velocity shear, possibly, and at that point, you can get, say, well, in that case, something like 2.5 times the load when the blade is at the top compared to a blade that's at the bottom. So it's a fairly extreme case of that. Then you've got to take into account the bathymetry and whatever islands or headlands are upstream, creating those eddies that are going to be shed off it. Then you've got waves. Yes, you get accelerations and decelerations as a result. You also get this variation in the angle of the turbine, the upstream velocity component, which will be fluctuating with itself up and down. And then, of course, the wakes. So you can measure your average velocity. Then you've got to take into the fact that it might be hit by larger scaled events. And then you've got turbulence on top. So you measure your average, bearing in mind it's a squared term. You could get instantaneous values that may be 3 times the average. Could even be a lot less. The problem with that is, if you actually are going to go from extreme to extreme, you're going to end up with a lot of fatigue problems. So you have the cycle through the velocity shear, fairly low frequency, waves in the environment, fairly medium, and then you've got turbulence. So let's look at that in terms of the high frequency loading then. So I'll try and break down each of those with what we've looked at. So we've looked at structural interaction. So the first thing we've done, we've created, the extreme case of a stanchion going all the way through, mimicking really the original MCT C-Gen, which had the pillar going all the way up through. And that's the worst case scenario you're going to get. And what we've done is we've moved the rotor in terms of the diameter of that stanchion, one diameter, which is L1, all the way out to 3 diameters away. So we've done it in steps, but show you the what we're getting. 3 diameters away, you're getting, it's fairly isolated from the effects of having a stanchion in place. When you get down to 1 diameter, you can see there are some fluctuations when the flow is hitting the turbine first and not the stanchion. If you reverse the flow, that power you can see is far more oscillatory. So automatically the power is going to come out, it's going to have to be cleaned up. The power companies do not like having fluctuating power. They want it fairly stable. On the on the loading side, you get a, well, very similar to the power, but the loading with regard to hitting the stanchion first and then the turbine blade, you get these massive fluctuations. That means those blades are going to be fluctuating a lot. The root will be subjected to fatigue problems. Flow misalignment. This is an ADCP set of data from one site. We've taken the value of the velocity above and we've tried to encapture the bulk of those flows, and that is giving you a plus or minus 20 degree variation. We've looked at that. What you actually get, the wake now comes off banana shaped, I suppose, and you get, for obvious reasons, a decrease in the power average, decrease in the thrust average, but a large increase in the bending moment that's translated through the blades to the end of the drive shaft. Again, those are then going to have to go through the seals, the bearings, and everything else. Any sort of wear and tear on those, failure can follow. Waves and currents. Well, if it works, it does. Simplistic this, you look at the streamlines or the arrows, you can see the effect on the velocity, you can see what it's doing to the wake, it's wobbling it up and down as you would expect, but that's just showing the effect. But the influence of that wave is very clear, and it's impacting on the turbine itself. So what does the wake do? Well, if you have a look at this, that's the individual blades, as is that. So we've produced this through a CFD line. Strathclyde have done this through a blade element momentum theory code, and they're very similar in the fact of what they're showing when you get a wave passing over. This means without a wave, that's what you're going to get, the fairly constant dashed line, and that slight ripple is because there's a stanchion in the way. The larger curves, you're getting a peak at the crest. So when the turbine blades are hitting the crest, that is when you're getting the high loads. That translates then to this bending moment problem. And you can see this is the angle for which the resultant force is actually acting, or moment. And this is the actual force in what it's doing. So you can see it's going from 150 kilonewton, oops, wrong one. It's going from 15 kilonewton meters up to 45 kilonewton meters over various rotations. And again, that's been looked at and put into a rotational orbital, and you can see you are getting extreme cases of these loads. So, automatically the waves are having an effect. So when we then go down into this deeper, we've run some experiments where we've run a turbine blade such that the blade is vertically upright in this one when it crests, the wave crests above it. And you can see the variation in the load that's coming across the turbine. If you look, if the blade hits at a trough when it's vertically upright, you get a much tighter loading variation. So this could come down to the fact that if you know what your wavelength is, you could arguably set a control mechanism that changes the rotational speed so you actually miss if the wave is suitably extreme. And this is just giving you an indication of the power under different conditions. So when the blade is hitting the crest, you get these load problems, but you also get this massive fluctuation in power as well. So we've looked at these sort of scenarios. We've done some a large-scale eddy-based modelling of them. So we've actually now got this. We've done some experimental studies on this and compared them to this. And we get of a similar sort of message on it. Now, the wakes are important because when you're actually designing your array, as I said, you really don't want an interaction of turbine and wake. So what does turbulence actually do for us? Well, the problem with turbulence is they can come with the different length scales, so eddy sizes, but you've also got this thing called turbulence intensity, so the root mean square value over a mean velocity. And when you actually plot out the turbulence intensity over the length scale, you can see the various effects on it. Large turbulence, great. You can get a fair amount of power out of it. But if you actually move then up, obviously you can't speculate about what will be up there, but you can make a rough estimate. large amounts going up, the higher your turbulence intensity, you'll get more average power out. But the problem is that's matched then with the loading. So there has to be a compromise. Back to these wakes, where there's next to no turbulence, a wake will recover 20, 25 diameters, rotor diameters downstream, increase the turbulence intensity. In this case, we're down to about 9 diameters. Increase it again, we're down to about 7. So therefore, turbulence does have a good effect as well, especially if you're looking at array packing. So, in order to show some of these things, what do? 3 tidal turbine models, each which are equipped with instrumentation that can actually measure the dynamic quantities that are coming out. Accelerometers on the stanchion, blade root strain gauges for thrust and torque, thrust torque measured on the drive shaft. Now they should equal the sum of the blades. We've got the power and torque that comes out from the motor. We're also strain gauged to the stanchion, so we can get that, and we can operate in speed and torque control. Now, full-scale turbines tend to be torque controlled. Scaled ones tend to be speed controlled. Big problem with doing speed control, it doesn't give you the extreme loads. The torque control doesn't react enough, so you end up with getting more loading when you have waves or turbulence. So we've done a series of tests. We've calibrated each of those turbines in Glasgow. We've done with and without waves in Rome, and also in Boulogne-sur-Mer at the Ifremer flume. We've also looked at various characteristics and upstream wakes at Ifremer again. We've recently just done a 3-turbine interaction at Edinburgh flow wave. So I'm not going to go into the huge detail on this, other than the fact the data rate for most of our sampling is 2 kilohertz, except for the accelerometers, which is 10 kilohertz, which is more than enough to capture the turbulence in wave-type activity that we're looking at. So those are the 4 facilities: the Insane, Ifremer, Acre Road, and I won't bother with that, and Flow Wave, which is a large facility in Edinburgh. So we've done some testing on it. We've got the characteristics, and then we've started testing. So that's just in a tow tank. I think it was Insian, and it's just operating. You set the carriage to go at a certain velocity. You've got still water, so there's no turbulence. So the characteristics are clean. We've then looked at putting waves in. So this is about a 4-meter wavelength. If you operate in torque control, the speed of rotation will vary depending on the velocity. If it's at speed control, it will stay constant. So the problem is when you have a tip-speed ratio, if you're in constant torque, this will actually move back and forward. If you're in constant speed, your torque will vary. So just quickly through this, we've got a number of cases that we've done some testing, and we've used the work that Blackmore et al. Did in Southampton. We've created some turbulence by putting different size grids upstream. So the first case, there's no grid, so the turbulence is, I don't know, 1.75, I think it was. So we have an inlet of 1.1 meter per second, but we measure a meter upstream of the turbine in order to get a decent value of what's actually hitting the turbine. So the second case, we put 1 grid definition in. Third case, we put a second definition in. So we've got various cases going through which end up with different turbulence intensities that are impacting on the turbine. The variation in the velocities is due to basically what we're putting in and the blockage just upstream of the turbine. Then finally, what we've done is we have put a turbine upstream with the turbine we're measuring off directly in its wake. Done a serious study of the velocity that is around here. Then we've offset the turbine so the tip of this turbine blade is in line with the hub of the upstream turbine. And we've then got background turbulence that's happening around there. The interesting thing with this, with the very low turbulence, that's your power spectrum density. So you're looking at how much energy is in the fluid. The peak comes down. This is with a wave number, 1 over m. That will give you your dominant eddy size that's going to impact on it. Then we go up to the different cases. And this is the ones with the turbines put upstream, in and out of the blades themselves. The interesting outcome of this, when the turbine's directly behind another one, because you have a deficit, the actual amount of power out and thrust is down. You get it off this, the average stays about the same, but your fluctuations in load and power are high. Hence, you don't really want it hitting or in contact with the downstream turbine. And again, so that's it operating with minimal turbulence intensity. It's a fairly nice clean flow that's hitting it. And then upstream of another turbine. And you can see this one's operating, I think, in torque control. So you can see that it's fluctuating in the speed that it's rotating at. So all of this adds up. If we expand this up to a 10-meter diameter turbine, for instance, operating in 3 meters per second of flow, then you're going to get to the equivalent of hanging 3 London taxis off the back end of each of these turbine blades. That's the sort of load if it's constant. The problem is you subject it to all of the fluctuations you can get, and you're going to be going to, I'll be generous, from that to hanging that off. And it's going to be going back and forward. Reality, it'll be less than that going to that. That's where the real problem comes with this. And it's no wonder that the first ones that went into the water never produced power because their blades were a little bit downstream of where the actual turbine was. And that went for, I think, about 3 of the big deployment cases. And finally then, we've put in 3 turbines. We've had 2 projects doing this. One was Southampton, where we had 2 different types of turbines in, and this is our 3 turbines from Cardiff. And we've separated the front ones in different distances apart, and we've put different distances for the upstream. And we've done power curves and various other loading things off it. And basically operating them, it's about a 1 meter per second flow. So I will say that in all of these facilities, the staff have been remarkably good at supporting us. And that's it. Thank you very much.
Okay, the time is over, but any simple question from... Oh, okay.
Well, the lorry is full and the taxi is full of people. They empty.
Why people?
Taxis normally have people.
Taxis do, yeah. Depending on what stormy day it was.
Seriously, why do you have to have the second turbine torque controlled?
You don't. We've done speed and torque control.
Why was it done?
Basically, the ones that are deployed are generally operating on a torque control. On the laboratory scale, we would traditionally operate them as speed control. The problem with that, Well, the reason for it is you get clean characteristic curves, and then the errors that are involved are down to the instrumentation you're measuring on. Whereas we've now shown that with torque control, so mimicking full scale, are actually resulting in some higher loads and torques as a result.